Welcome to the seventh recorded lecture in the sequence of lectures on undergraduate analysis. So we'll be talking about uniform continuity and Lipschitz continuity, strengthened forms of continuity here. The Lipschitz continuous is usually not covered or presented in a lot of undergraduate analysis courses. I'm supplementing that. I think it's really important. And in fact, most of the functions you deal with are Lipschitz continuous, which are implying uniform continuity, as you'll see in this lecture. This material corresponds to chapter 3 sections in Ross. I'm not going to list these section numbers anymore. I think they're pretty easy to find from the table of contents or index if you're looking in that book that I've been talking about, Kenneth Ross's Elementary Analysis, Theory of Calculus, through these recorded lectures. And the material, again, I'm drawing from corresponds to the written lecture notes that also supplement the Ross textbook. So without further ado, we're going to jump right into it. The main take home that you're going to get from these two definitions is that you're defining the property on the entire set. So you're just saying you kind of don't care about what points you pick in the set, subject to the points being essentially close together for uniform continuity, or just any points in the set for Lipschitz continuity. Whereas our pointwise continuity was defined, our original continuity, our characterizations, both sequential and epsilon delta, were continuity at a point. We had to say F was continuous at a point in its domain if. Here we're saying, hey, it's continuous, uniform, like for instance, uniformly continuous on a set, right? So it's on the set. It's a property of F on the set. If for every epsilon greater than 0, I'm going to switch real quick to red. Sorry about that. If for every epsilon greater than 0, there exists a delta greater than 0, such that for every x and y with absolute value of x minus y less than delta, we have absolute value of f of x minus f of y is less than epsilon. So this means that the delta only depends on epsilon, whereas our original definition, the original epsilon delta definition, the delta could depend on both epsilon and the point x that you were saying f was continuous at. Here we're saying for the whole set S, there is one delta that works for every single point in x, y, so that if an x and y are chosen from where f is defined and their distance is less than this delta, then the distance between the output values will be less than an epsilon. All right, that's what uniform continuity means. Lipschitz continuity says that there's some constant L greater than or equal to 0. It might be 0. The function was a constant function, such that for any x and y and s, and they could be really far apart, we have that the difference in the function values is bounded, right? It's less than or equal to the distance between the inputs scaled by L. So if x and y get farther and farther apart, then L times absolute value of x minus y gets to be larger and larger and larger. So this is not necessarily a sharp bound. How do you actually choose this in practice? If I just gave you a function f and I said it's Lipschitz continuous, how do you think you'd prove that? You have to come up, right? The first thing we have is a there exists. How do you typically come up with that? Well, if it's a continuously differentiable function, here's what you basically do. You differentiate the function and you hope that the derivative is bounded on the set you're talking about. If the derivative is bounded on the set, take the absolute value of the derivative and bound that. Or take them, if the maximum exists, take that. And if you can do that, you take that value to be L, whatever that bound is. Because if you imagine taking this inequality, rearrange it, divide by absolute value of x minus y, so assume that x and y are not the same point, then you have something that looks like f of x minus f of y over x minus y. If you were to take the limit as y approached x, that would look a lot like the derivative of f at x. Right? So there's some sort of relationship for continuously differentiable functions with the value of L and a bound on the first derivative. All right, that's conceptually how you often think about this. But of course, we can have non-differentiable functions that are also Lipschitz continuous, in which case it becomes kind of problem dependent how you might construct the L. But if the F is differentiable, like in the sense you learned in a basic undergraduate calculus class, then take the derivative and bound the absolute value of the derivative. And if you can do that, take that bound, take it as your Lipschitz constant L. All right. Now, it's easy to see that Lipschitz implies uniform continuity. In fact, it gives a recipe for how to pick delta. So pick delta to be epsilon over L plus 1. Why, again, divide by L plus 1? L might be 0. I don't want to divide by 0. So basically, once you've picked an epsilon, consider any epsilon greater than 0, let epsilon be greater than 0, then this is how you construct your delta. And then you say, hey, look, if x minus y is less than delta and f was Lipschitz continuous, then that means that absolute value of f of x minus f of y is less than or equal to L times x minus y, right? It's just straight from the definition right there. And then I say, well, look, x minus y in absolute value is chosen to be less than delta. So this is now strictly less than L times delta. And based on how I chose delta, I know that L delta is equal to this L times epsilon over L plus 1. And L over L plus 1 is less than 1. So that's less than epsilon. So there's your very simple proof, just the outline of the idea, really, of why a Lipschitz continuous function is uniformly continuous. So Lipschitz implies uniform, which implies pointwise continuity. And you can only reverse these directions if additional conditions hold. And I want to give an example that kind of explains what the issues are and how you might need to be able to go back, from one direction to another, where you can spot what the issues can be with the continuity. Okay, so here's my first kind of pair examples. F of x equals x is Lipschitz continuous on the whole real line. How can I see this? Well, differentiate f. Or what's the recipe for picking the Lipschitz constant? If I differentiate f, it's 1. Well, 1 is bounded. It's a constant function 1. That's going to be your Lipschitz constant. You can show this. In fact, what is f of x minus f of y? It's x minus y. So the absolute value of f of x minus f of y is less than or equal to the absolute value of x minus y. So the Lipschitz constant there is 1. Very easy to do that directly. You don't even need to take the derivative. I'm just trying to show you how the Lipschitz constant is related to the derivative. But f of x equals x squared is not Lipschitz continuous on R. And conceptually, you could see this by saying, well, what's the derivative of a function like x squared? It's 2x. Well, that's something that goes to infinity. That derivative is not bounded on R. But it is a function that's bounded on any bounded subset of the reals. So if I was just considering the function f of x equals x squared on, let's say, the interval 0 to 1, or even 0 to a million, I could find a Lipschitz constant. If the S was an interval, let's say 0 to a million, so if that S was 0 to a million, that's a bounded set, I would take the Lipschitz constant to be 2 million, because 2 times x, the derivative of x squared, that's the largest value we can get in magnitude on the set 0 to a million. It's 2 million. All right, what about f of x equals the square root of x? This is not Lipschitz continuous on 0 to infinity, with including 0, but it is uniformly continuous on that set. So why is it not Lipschitz continuous? If you can differentiate it, you can check. If I differentiate the square root of x, I see that its derivative looks like 1 over 2 square root of x, which has some sort of behavior like asymptotic. That's a bad graph. It looks something like this, 1 over 2 square root of x. And it goes to infinity, right, as x goes to 0. The derivative is only defined on the open interval 0 to infinity. And so there's just no bound for the derivative. And so there's no way I'm going to find a Lipschitz constant. This is a result that you want to prove, but we're just going to use it as if we know it's true. But it is Lipschitz continuous on a to infinity if a is strictly greater than 0. So if I just go out from 0 a bit to find an a, and then I go up and say, hey, that's the largest value the derivative can ever be, that's what's going to be your Lipschitz constant on that interval a to infinity, even on an unbounded interval. All right. What about f of x equals 1 over x? This is not uniformly continuous on the open interval 0 to infinity, but it is pointwise continuous on 0 to infinity. And it's certainly not Lipschitz continuous either, right? If I take its derivatives, they're also unbounded on this interval. But it is uniformly continuous on a to infinity, again, if a is strictly greater than 0. I'm not going to go through the proofs of this, but the main idea is if you have a function that's going to infinity at a finite number at some endpoint of a half open or closed interval, then that's generally a recipe for disaster for why something's not going to necessarily be uniformly continuous. There are examples that are uniformly continuous, but you have to, the proofs are not necessarily trivial. There is a little bit of work involved with that. So let's get some results. We're just going to hit these main points. These are going to be presented without proof. If you have a continuous function on a closed interval a to b, then that means that f is uniformly continuous on the closed interval a to b. So that says something about if I just am describing a function f, let's say, on the open interval a to b, but I say, you know what, if I included a and b, it wouldn't be a problem. maybe F's not defined at those endpoints, but I could extend F to be a continuous function on A to B by, let's say, just defining a new function that's equal to it on the open interval, and then it's equal to the limits of F if they exist as real numbers at these endpoints. Then I have a uniformly continuous function. This is a result that's proven in all the classical books on this subject. I believe it's in Ross as well. So that's nice. But then that tells you if you can't really get it to be continuous on a closed interval, it's probably not going to be uniformly continuous on a closed interval because, well, uniformly continuous would have to imply continuous, for example. And then if you have a uniformly continuous function on a set and you consider some Cauchy sequence in the set, then the sequence of function values is itself a Cauchy sequence. And the first example I shows the necessity of the function f being uniformly continuous. All right, you cannot drop the uniformity of the continuity, and theorem what I listed here is 13, and still have this result be true. This is what the first example shows. If you consider the function f of x equals 1 over x on the half open 0 to 1, closed on 1, then I could define the sequence of inputs on that interval to be 1 over n, which clearly goes to 0, right? And I know that sequences of real numbers are convergent if and only if they're Cauchy. So convergence and Cauchy are like equivalent. They're the same idea on the real number line, just in different forms. Well, if 1 over n goes to 0, and that's xn, f of xn, which is 1 over x, is just going to be n, which diverges to infinity. Convergent sequences are Cauchy, Cauchy sequences are convergent, but this is a divergent sequence, so it cannot be Cauchy. All right? But it is a continuous function. F of x equals 1 over x is continuous on the set, but it's not uniformly continuous. I cannot extend it to be a continuous function on the closed interval 0, 1. There's no value that I could assign the limit as a real number as x approaches 0 because it goes to infinity. That's the problem. All right, here's another example. Consider f of x to be sine of 1 over x. You've probably seen this in the book already if you've been reading it, something like that. It's something that starts to kind of like oscillate. As you approach 0, it just oscillates really, 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 really fast, right between -1 and 1. Okay, so if I again consider some sequence of inputs, I show it here, 1 over pi over 2 plus pi times n. That's all in the denominator. As n goes to infinity, xn goes to 0. All right, so again, xn is Cauchy. But sine of 1 over x, well, that's just going to be 1 over, this 1 over pi over 2 plus pi over n. So it's just going to be sine of pi over 2 plus n times pi. I just rewrote it as n times pi instead of pi times n there. And when n is odd or n is even, I'm either going to get basically up like sine because of the cyclical nature of how sine is evaluated. It's either going to be just like sine of pi over 2 or sine of 3 pi over 2. So it's just going to be like, bouncing between -1 and 1. All right, so when n is 1, it's pi over 2 plus pi, it's a 3 pi over 2, which is -1. When n is, let's see, even, then it's just like I'm evaluating sine of pi over 2. So again, that's a divergent sequence, not Cauchy. But this function, which you've probably seen if you did some of the initial exercises in chapter 3, this is a continuous function at x equals 0. Right? So I basically take x times sine of 1 over x on 0 to 1, not including 0, because it's not defined at 0, because you have a 1 over 0 here if you try to plug in x equals 0. But it does kind of, if you were to graph it, there's the lines like x and -1 over x, and it kind of just does this. And it has a limit that's a real number of 0 here. And so you define a new function that's equal to 0 at x equals 0. And this is a continuous function. And so now what happens? I take that same sequence from before and I plug it in. And what happens? I get function values that are also convergent and Cauchy, right? And because it's a continuous function in general, f of x that we have, the theorem 12 and 13 guarantee this to be true for any Cauchy sequence, right? Not just this particular one that I picked here. So that's it, just trying to get you some idea of strengthened notions of continuity and how they're connected and which ones imply which and what issues to watch out for. So short lecture, but that's going to be it on chapter 3. I'm going to be moving on in Ross to material in chapter 4 and then chapters 5 and 6. And we're more than halfway done with reviewing this undergraduate analysis material.